Hi, so this video is going to go over section 6.2, which is titled the Binomial Probability Distribution. So this will be the last section we'll cover in chapter 6. So the first thing that we want to do is just talk about what a binomial probability experiment is. So you can see here the binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive or disjoint outcomes. These two outcomes are generally referred to as success, such as making a free throw, and failure, such as missing a free throw. So experiments in which only two outcomes are possible are referred to binomial experiments, provided that certain criteria are met. Right? So the criteria that must be met are the following. Right? There's 4 criteria. So the first is that the experiment must be performed a fixed number of times. So each repetition of the experiment we call a trial. Number 2, each trial has to be independent, right? So that means that the outcome of one trial won't affect the outcome of the other trials. The third thing is that for each trial, there are two mutually exclusive disjoint outcomes, right? So we either have a success or a failure, and there's no overlap, right? There's no like in the middle, like this could be a success and a failure, right? It's either one or the other. And then 4, the probability of success has to be the same at each trial of the experiment, right? So when I do it once, that probability has to stay the same if I do it second time, a third time, fourth time, and so forth. So if we let the random variable capital X be the number of successes and n trials of a binomial experiment, then X is called a binomial random variable. So before we look at how to compute these binomial probabilities, I want to introduce some notation. So the notation that we want to look at is that n represents the number of independent trials of the experiment, right? So n equals the number of trials. I want to let p denote the probability of success for each trial, so that 1 minus p is the probability of failure for each trial, right? So in other words, the probability of success, we're going to let be equal to lowercase p, right? So that means the probability of a failure is 1 minus p, right? Because, those are only 2 options and they have to add up to 1, right? And then lastly, we're going to let the capital X variable denote the number of successes and independent trials, right? So little x is going to take on those possible values, right? So we're going to let little x be the number of successes. Right, so we're going to be finding like probability of some x value, right, is what we're going to be trying to find. So this x value of successes has to be in between 0 and little n, right, because n is the number of trials we do. So if I only do 10 trials, I can't have like 12 successes, right? It can't be bigger than the number of times I do the experiment. Right, so then this next example is going through some probability experiments and trying to decide if it's binomial or not binomial. So part A, it says a random sample of 15 college seniors is obtained, and the individuals selected are asked to state their ages, right? So typically, age is a continuous variable, right? And also it's not clear if there's success or not, right? So this situation would be not binomial, right? And we can say that the random variable age is continuous, right? So it can't be binomial if it's continuous, because a binomial variable is discrete, right? That's what this chapter focuses on, is discrete random variables. Part B says an experimental drug is administered to 100 randomly selected individuals, which the number of individuals responding favorably recorded, right? So we want to go through this checklist of 4 items and see if this is binomial, right? So the first item is, is it performed a fixed number of times? So it is, right? It's performed 100 times, so that checks that box. The second condition is that the trials need to be independent. So it's reasonable to assume that one trial is not going to impact another trial, right? So like one person taking a drug is not going to impact the results of another person taking that same drug, right? So those would be independent. We need success or failure for the third item, so outcomes. So that seems to make sense, right? So maybe the drug is meant to lower your blood pressure or something, right? So either it did that or it didn't, right? So success or failure, that seems likely. And then we need a probability of success to be the same for each trial, which makes sense that would be true here, right? Because you're giving the same drug to the same, not to the same people, but you're giving the same drug out each trial, right? So that you're not changing anything, right? So this seems to be binomial, right? So the second one, or the next one, part C, it says a poll of 1,200 registered voters is conducted in which the respondents are asked whether they believe Congress should reform Social Security. So we can go through that checklist. So are there a fixed number of trials? There's 1,200 trials, right? The trials need to be independent. So that seems to be reasonable, right? We're polling registered voters. It's likely that one person's not going to impact the other person's opinion, right? Success or failure needs to be the outcome, so that would be true, right? Either you believe or don't believe, right? We're kind of forcing them to pick yes or no, and then the probability of success would be the same for for each trial, right? So this would also be an example of a binomial experiment, right? So then part D. It says, in a town with 400 citizens, 100 randomly citizens are asked to identify their religion. The number who identify with a Christian religion is recorded. So this situation would actually be not binomial. And that's because the trials are not independent. Right? So since we're focusing on looking at just the town and we're randomly selecting the people in the town, that's what makes those not independent. Because if you think about it, in a given town, especially a small town, there's going to be limited options on the types of churches or synagogues or religious institutions available to you, so it's likely that your results they're going to impact each other in that sense, right? Right, so this exercise was just to help you get familiar a little bit with this criteria, right? So we need these criteria to be met for it to be binomial. Right, so then this is a note that I want to make, is that just because, so it says, note that the word success does not necessarily imply something positive, right? So success means that an outcome has occurred that corresponds with P, the probability of success. For example, a probability experiment might be to randomly select 10 18-year-old male drivers. If capital X denotes the number who have been involved in an accident within the last year, the success would mean obtaining an 18-year-old male who was involved in an accident. The outcome is not positive, but is a success as far as the experiment goes, right? So what we want to pay attention to is that a success means a success for the variable, right? It doesn't necessarily mean that it's positive, right? So make sure you understand that. All right. All right, so example 2, this is an exercise to help us kind of see where the equation for calculating a binomial probability comes from, right? So there's an example similar to this in the textbook as well. This is a different one, but is, like I said, similar. So it says, according to the Bureau of Transportation Statistics in April 2019, the proportion of on-time flights at Las Vegas's McCarran International Airport was 0.8. Suppose that 4 flights were randomly selected from April 2019, and the number of on-time flights X is recorded. Right? So it's important here, just to make note that this 0.8 value is going to be the probability of success. Right? In other words, my lowercase p, right? Or probability of, I'll use capital S for success. That's what we're using here in this diagram, is 0.8, right? So that means that a probability of a failure is 0.2, right? Because they have to add up to 1. So that'd be 1 minus 0.8, which is 0.2. So that's just using the complement rule, right? So there's only 2 options in binomial. So then what we have here, let me zoom out so you can see the whole thing. Right, this is a tree diagram, right, showing the possible scenarios that we could have. Right, so the first trial we could have a success or failure, right? The plane could be on time or not. And then the second trial, if I had a success the first time, it could be successful again, or it could be a failure. And same with failure, right? So we just go through each of those, break down as being a success or a failure, right? So then this last column is little x. It's the number of successes, the number of s's in each outcome, right? So this lists the outcome where, like the first letter denotes the success or failure of the first plane, the second letter denotes the success or failure of the second plane, and so forth. And then in this column, we're just counting the number of s's, the number of successes, right? So we have 4, 3, 3, 2, and so forth, right, going down. Right? All right, so we want to create a probability distribution for this situation, right? So remember that a probability distribution is a table, right? It's going to be a table that shows all the possible outcomes of the random variable and its corresponding probability, right? So here's my x values, my possible outcomes. Here's the probability of that happening, right? So x in this case could take on 0, 1, 2, 3, or 4. Right, because we have 4 planes. So either 0 of them could be on time, 1 could be on time, 2 could be on time, 3 could be on time, and 4 could be on time, right? So what I need to do now is I need to fill in the corresponding probabilities of x happening, right? So we can do this using methods from chapter 5, right? So the first thing, if we look at what's the probability of x being 0, right? Or in other words, what's the probability of 0 happening, right? So 0 planes are on time. Well, if you look at the tree diagram, that would be this outcome here that I just circled at the bottom, right? The very last one. That means that all planes were failures, right? They were all late, right? So this would be equal to the probability of F, 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 F happening, right? So remember from last time, what this is referring to this notation, this would be equal to the probability of the first plane being late, a failure, and the second plane being a failure, and the third plane being a failure, and the fourth plane being a failure, right? And these planes would be, the first, second, third, fourth planes being on time or not, they would be independent of each other, right? So we can use the multiplication rule for independent events, right? So we're going to use the multiplication rule for independent events, right? So that would give me the probability of f, right, for the first plane times the probability of f for the second plane times the probability of f for the third plane times the probability of f for the fourth plane, right? And we already noted that the probability of f up here is 0.2, right? So this ends up being 0.2 times 0.2 times 0.2 times 0.2, right? Which is 0.2 raised to the fourth power, which comes out to be 0.0016. Right? So we could fill that in on the table. All right, so then the next one that we could consider is what's the probability of x equaling 1, right? That's the next row on our probability distribution table. So again, this would be the same thing as the probability of 1, right? We could denote it that way as well. So if I look at the tree diagram, I want to look at all of the outcomes that have one success. Right, so that could be this one, this one, this one, or this one. Right, there are four options. Right, so this would be equal to the probability. Whoops. Of S, F, 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 or F, S, F, F, or F, F, S, F, or F, 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 S. Right? In other words, we want just one S, so you're just kind of moving the S through, right? Either the first plane was on time, the second place was on time, the third plane was on time, or the fourth plane was on time. Right, if we want just one plane on time. So then these would be disjoint or mutually exclusive events, right? So we could use the addition rule here, right, from chapter 5. So we can apply the addition rule for disjoint events, which would give me the probability of S, F, 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 plus the probability of F, S, F, F, plus the probability of F, F, S, F, plus the probability of F, 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 S. Right? So then now what I can do is same thing as the first one when x was 0. Right here, right, I can apply the multiplication rule for independent events and break these up, right, where this just becomes, this first one would be the probability of S times the probability of F times the probability of f times the probability of f. Then we'd have plus the probability of f times the probability of s times the probability of f times the probability of f, right? And then plus the probability of f times the probability of f times the probability of s times the probability of f, and then plus the probability of f times the probability of f times the probability of f times the probability of s. Right? So one thing you'll notice is all four of those things are going to be the same probabilities, right? So I have four of them that are the same, and it's going to be the probability of f raised to the third power, right, times the probability of s, right? That's going to be true in all those cases, right? So like in the first one, there's one probability of s and then 3 factors of probability of f, right? And in the second one, there's one probability of success and 3 factors of probability of f, right? Which makes sense, right? In each case, we have 3 planes that were not on time and 1 plane that was on time, right? So filling this in, this would be equal to 4 times probability of success is 0.8, and then the probability of failing is 0.2, and we can raise that to the third power, right? Right. So when I wrote this, I just wrote it as 4 times the probability of s times the probability of f raised to the third power, right? We can do that because of the commutative property of multiplication, right? It doesn't matter the order we multiply things in. So when I go to simplify that, right, you can plug that in your calculator. You should get 0.0256. Right. So then next, we could calculate, what's the probability of x equaling 2? Right. So if I let me erase this highlighter. Right. So we want x equals 2. So we're looking in this last column and looking for all the outcomes. That's a 2 successes. And there are 6 of them, 6 successes, right? So what you should start to see is that what you're going to do is notice we're counting that we have 6 different options to have 2 successes. And then we need to multiply. This would be the probability of s. And then here, this would be the probability of f having a failure. So there were, if we have 2 successes, there, well, this value would be 0.8, and this value would be 0.2, right, from what's given. And then the exponent would be how many successes occurs, right? So this exponent here would be the number of successes, and this exponent here would be the number of failures. Right? So if x equals 2, there's 2 successes, and that leaves that 2 planes weren't on time, right? So this would be equal to, so if you plug that in your calculator, you should get 0.1536. Right, so then the next one we need to do is what's the probability of x equaling 3. So again, we're gonna fill this in, right? I need a number here, which is going to be the number of ways to get 3 successes. And then we're going to have, in here is going to be the probability of S, and then in here would be the probability of F. So we know those would be 0.8 and 0.2. And then we're going to raise these exponents to, so this one would be the number of successes that we have, and this one would be the number of failures. So I could fill those in too, right? Because if x equals 3, this will be 3. And then the number of failures would, there'd only be one plane that would be failing, right? So if I look at the tree diagram, right, so let me erase this. So then the number of outcomes that have 3 successes would be these. Right, so there should be 4 of them. Right, so this value is 4. Right, so we're able to fill that in. So if you multiply that in your calculator, you should get 0.4096. Right. So then lastly, the probability that x equals 4, right? Again, what would go here would be the number of ways to get 4 successes. And then we would have here the probability of having a success, here the probability of having a failure, and then this would be the number of successes, would be the exponent, because you'd have that many factors, right? And this would be the number of failures. So, you can look at the tree diagram, but the number of ways to get 4 successes is just going to be 1, right? Because that's SSSS happening, right? That's the very first outcome. The only way for all 4 to be on time is if all 4 are on time, right? And then the probability of S is 0.8. The probability of F is 0.2. 0.8 would be raised to the 4th power because we have 4 successes, and there would be 0 failures then, right? So that would be raised to the 0 power. So if you plug that into your calculator, you should get that equals 0.4096. Right? So this table was what we were after. That's the probability distribution. Right? So it turns out that we can actually count the number of ways that the number of successes can happen by using a combination, right? Because in a combination, remember, order doesn't matter, and that would be true in this case, right? So if I have F F S F, that's the same. So if I had F F S F, that's the same thing as F S F F, right? In both cases, there's 1 success, right? So we'd use a combination, because the order doesn't matter, right? So the probability of obtaining X successes in N independent trials of a binomial experiment is given by the following formula. So P of X is equal to N choose X times P raised to the X power times 1 minus P raised to the N minus X, right? And this is just what we were talking about, right? So this part here counts the number of ways to have X successes, right? This P value, of course, is the probability of success, right? And that's raised to the number of successes, x. And this n minus x, that's going to calculate how many of the items, right? Because there's n trials. If I take n minus successes, the rest were failures, that's going to give me the number of failures. And the 1 minus p, of course, remember, is the probability of a failure, right? So through that last example, we kind of explored how to come up with this equation, right? And then this next table is just reminding us of some mathematical phrases that you want to be comfortable with. So given a certain phrase, how does that translate into a math symbol, right? So if you're not good with that, make sure you look over that table 9 and try to get comfortable, right? We'll try some examples to practice this as well. Right, so in example 3, so we want to calculate a probability of a certain binomial experiment, right? So these first few examples, we're just going to get comfortable with making the calculation. It's not in context, right? So we're given n, p, and x, and we want to calculate the probability, right? So in this case, right, we would have the probability of little x equals 3, which would be the same thing as the probability of 3, right? Which this equals, using that equation, would be, we'd use a combination, right? 10 choose 3, right? We're choosing 3 successes, 10 items, and then this would be p-value 0.4, and that would be raised to the number of successes, and then we need to multiply that times the probability of getting a failure, which would be 1 minus 0.4 or 0.6, right? So that's 1 minus p in there. And then what would be the exponent would be the number of failures that we have. So if we're doing something 10 times, we had 3 successes, that leaves 7 failures. Right? So don't forget that to calculate, usually we use n choose r for a combination. Remember, this is equal to n factorial over r factorial times n minus r factorial, right? So in other words, this would be equal to 10 factorial over 3 factorial times 10 minus 3 factorial. Right, and then this would be times 0.4 raised to the 3rd power times 0.6 raised to the 7th power. Right? So if you plug that in your calculator and simplify, this comes out to be 0.214990848, or approximately 0.2150, right? If I round to 4 decimal places. Right, so don't forget from chapter 5 how you can input that in your calculator or StatCrunch. Right? Or you could simplify by hand, right? We looked at doing examples like that as well. So now what I want to do is show you how you can calculate this in StatCrunch. So what you're going to do is go to the Stat menu, and then go to calculators, and then we want binomial, right? So this will give me a binomial calculator. And then down here, you're going to fill in, your inputs, right? So right here is going to go your n value, which is 10. Here I'm going to plug in 0.4 for p. And then the probability I'm finding is I want x to be equal to 3. Right? So I just need to change that equality symbol and the x value, plug that in, and then hit compute, and it tells me right here, right, this is like my output box, this tells me that probability, right, which is what we just calculated by hand. And this gives me a nice graph of the discrete probability distribution, right, and it's just reminding you that I'm finding this part in red, right? I'm trying to find that probability in red. Right. So using StatCrunch, right, we still found that the probability of x equals 3 is equal to approximately 0.2150. Right? All right. So now, what I want to show you is how to find this probability using a table in your text. Oops, didn't mean to go to my courses. All right, so I'm just going to click on a random section. Come on. All right, so I'll open up the eText. All right, so I'll just go into the appendix, appendix A, and we want table 3 for this case. Right, there's table 3 and 4. So you just have to be familiar with how the table's arranged. The first thing you want to do is look on the very first column is n. So you want to find your n value in the table first, right? And then you're going to find the particular p-value that you're looking for. And then you're going to go down to the row that matches up with the x value, right? The number of successes that you're looking for, right? So you have to be, again, just comfortable with this table. So we had an n value equal to 10, so I need to find the n value of 10, which is this page here, right? So I'm going to just going to print this page. So I'm going to save it as a PDF. So I'll just save this to my downloads. And I'll just call this n equals 10. Right? So I'm doing this so I can write on it. Might be a little easier to show you if I can draw on this. All right, so just as a reminder, we were trying to find the probability that x equals 3, and we had n equals 10, and p equals 0.4, right? So I'm going to be, this column here, p equals 0.4, so it's going to be some value in this column. Here's my n equals 10. So then my x value was 3, right? So that would be this row. So then where those intersect, right, there's my magic number that I'm looking for, right? The probability that x equals 3 in this case is 0.2150. Right, so that matches up consistently with what we found in StatCrunch, the table, and what we calculated by hand. All right. All right, so we still got the probability of x equals 3 is equal to 0.2150. All right, so the next one, part B, is we're given n equals 9 and p equals 0.2, but this time x is less than or equal to 3, right? So something that we have to understand is we're finding the probability. Oops, come on.